for joining, and thank you especially for our speaker today. This is Associate Professor Daniel Schmidt from Monash University, and we'll be talking about time series classification.
Thank you. Yes, so I'm from Monash University, which is a large university in Australia, if you're not familiar with the university. And it's actually one of the biggest, perhaps the biggest university in Australia, but it's certainly in the top couple. And I'm from the Department of Data Science and AI, which is part of the Faculty of IT. We have an IT faculty at Monash. And one of the big departments is Data and AI. And I'm actually here on sabbatical. I'm visiting in Taiwan. I've been to Finland before, but a long time ago, 2011. So it's nice to come back, and the weather until today has been, behaving, but I think for the rest of the week it's supposed to be pleasant. So. Cool. So I'm going to be talking about fast and effective time series classification. So yes, so outline of the talk. Look, it's a lot of slides. I'm not sure how much exactly we'll go through, as I sort of time a little bit shorter than I sort of had anticipated. I didn't read the email probably, but anyway. So what I'm going to do is talk a little bit about time series classification as a problem, and then I'm going to cover two methods. One is called Rocket, and one is called MINIROCKET. So the first method is one that I wasn't directly involved in, but changed, I suppose, the scene in the time series space. And then MINIROCKET is an extent. Well, we took this rocket idea and reduced it down to its essentials and produced this technique called MINIROCKET, which is an extremely fast method for time series classification. So Rocket was a big change in the speed at which time series classification could be done at scale, and this MINIROCKET technique kind of reduced it to its essentials and managed to speed up things even more dramatically. So that's basically what we're talking about, some techniques that are very effective at scale in space and time series classification. And if we have time, I'm going to discuss this idea of pre-validated ridge regression as a very fast technique to approximately fit high-dimensional multinomial regression models. So, in time series classification, basically it's a specialized form of classification problem where you have a bunch of individuals, they have some L plus labels, and the features are one or more time series. So attached to each individual is one or more time series. And of course, they don't have to be time series per se. You know, the concept of time isn't particularly important, but there has to be some sort of dependency between the indexes of these sequences. So they could be spatial relationships, or you could even just think about it maybe as some type of functional classification, where you have samples from some function, and there's some index that serves the role of a time type index, and these are your features. So common examples of problems might be, for example, in satellite imagery, you have the pixels change over time with the satellites, and they form a time series of intensities or colors. And you can use this to try and classify whether there's sorghum or wheat or corn growing in a particular plot of land, or whatever happens to be there, forests, different types of forests and the rest. Another example would be in something we're working on, epileptic episodes from neural measurements. So you have neural measurements and you're trying to predict if there's going to be an epileptic episode in the next 10 minutes or whatever. So there's lots of different applications for this type of problem. And throughout the rest of the document, throughout the rest of the presentation, I'm going to assume that there's just a single time series associated with each individual. It's not super important, but it just makes things a lot easier to explain and present. And we can assume that the time series are all the same length. Again, this is not necessarily the case in practice, but it just makes things a little bit easier. So I'm going to denote the targets by Y and these features, which are our time series, by X. So every individual has some time-ordered sequence of measurements associated with it. And the aim, of course, is to classify individuals on the basis of these time series, right? They're our raw features. So there's lots of different techniques for time series classification. And neatly in the space, there is a benchmarking data set called the UCR, the University of California, Riverside time series repository, which has, well, it has more than 112 problems, but I say 112 because a lot of the early assessments was done on 112 different time series problems that were collected from different domains, different sizes, a different series length, and so on. So this has been, I think, a really useful thing in this space because it's allowed people to rapidly test new ideas and benchmark them against existing ideas in this sort of, not self-contained, but at least this little worldview where you can get a bit of an idea of how things are performing. And in a very structured fashion, so it's quite easy to recreate other people's results in this space. I think it's been a really important aspect of the area, though I do think to some degree perhaps the idea of using repositories or overusing repositories maybe is not a great idea, can stifle development. I think it's a very good way of rapidly accelerating the development of an area or problem in initial space. So as an I'll cover a few of the important techniques in the space, just as an example. So one of the earliest techniques was nearest neighbor classification with something called dynamic time looping, which is effectively a rediscovery of the edit distance algorithm. So you take two time series and you see how close they are by doing some sort of time warping to match key features. Then you do nearest neighbors. And on this UCR data set, or this UCR repository, which has, as I said, over 112 problems, pre-divided into various training and testing folds. This scores about an average of about 0.76 classification. So that was one of the earliest methods. The next three here are what you might have considered state-of-the-art, maybe pre-2020. So there's a method called TS-Chief. I don't know what the actual stands for, but it was a thing called a proximity forest. So it used distance measures between time series to build forests of trees. We have, of course, deep learning. So in 2019, this inception time architecture was introduced as which is probably the baseline deep learning architecture in this time series classification space. And look, there's been plenty of development since. I guess I don't want to go too deep into why some of them may be a little bit difficult to exactly determine how well they perform, but this inception time you can kind of consider to be the baseline go-to structure for deep learning in this space, and it's a multi-level convolutional neural nets with some fully connected layer at the end. And then there's HIVE-COTE, which is a hierarchical ensemble classifier. So it's actually got 4 or 5 different techniques in there, including something like shapelets, which is a kind of like a generalization in some sense of wavelets. A little bit, we could think about that. And this is currently the method that attains the highest average classification accuracy in the benchmark, or in the repository, in the benchmark. The TS-Chief, the proximity forest, and the deep learning have roughly similar performance. HIVE-COTE is almost 90% average accuracy. Now, the thing is, this HIVE-COTE method is very, very slow. So if you were to have a look at the rough sort of wall clock timings to run these state-of-the-art methods on the whole 112 data sets, this was in 2021, so the exact times, of course, are going to depend on the hardware that you have, but it's a rough idea of sort of the orders of magnitude. So the neural nets, or the deep learning structure, took about 4 days to train and predict on all 112 problems on some GPU cluster. So it's not exactly comparable with the others. There's probably a little bit more power in there, but roughly in a 4-day time. The proximity forest took about 2 weeks when run on a commodity PC, and HIVE-COTE 3 takes about 3 weeks, and that's with, I believe, a hyperparameter set to limit the amount of time that's run. So you get the highest classification accuracy at a very expensive price. And in general, what you would find, there's lots of other methods. In general, what you would find is the faster the methods, as I said before, 2020, the faster the methods were, the lower the accuracy they had. So you really did get this trade-off in this particular space. It was very evident. So now I'm going to introduce this method called Rocket, which is based on random convolutions. So in 2019, 2020, my two collaborators at the start, Angus Dempster and Jeffrey Webb, they introduced this idea of this architecture they call Rocket. So basically, they just stripped the problem back and said, we're going to have a single shallow layer network, and the network is just going to consist of a bunch of random convolutions. And then we're going to use a linear classifier at the end to bring them all together. So in this space, we have k randomly generated convolutional kernels of random lengths, 7, 9, 11. A lot of this was a little bit, well, I wouldn't say it was super empirical, but it turns out a lot of these hyperparameters, the method is relatively sensitive to them. And so these are sort of the default settings in the package. The coefficients for each of the kernels were randomly sampling just from a normal, and then zero mean to make them invariant to level shifts of the time series. And then random dilation was picked, so the kernels were scaled randomly. And they were just single bank of shallow kernels. And then for each of the series, they computed convolution between the kernel and the series. So we have these moving average filters. So we just do a convolution to get a filtered signal, and they use two simple pooling features at the end of it. The first one was the maximum value across the filtered series, and the second feature was what they call the proportional positive values, which was the number of times the filtered sequence exceeded some bias, which was also randomly set. So, yep. Beg your pardon?
How do you select different kernels here?
So the kernels are just randomly generated, the weights are randomly generated from, in this case, a norm.
But how could you deal with this some short-term and long-term different dependencies among the?
So we have, in addition to this, there's a random dilation aspect. So the kernels are chosen to be 7, 9, or 11 weights long, and then are randomly stretched or dilated. Yep. So there's no, yeah, that's it. That's the way that multi-scale analysis is done, by simple dilation.
Okay, so not for practical. It's not a real world data.
All this data are real, so all these problems are real world data problems. So the benchmark is all comprised of 112 real.
Yeah, very much.
Cool. So, I mean, I'm assuming most people know what convolution and all the rest does, but, you know, for those who may not, or may not be 100 across it, I've still a little bit of a graphic. So, if you have a moving average filter and you convolve the signal, effectively what you're doing is moving the kernel across the signal and computing the inner product between the kernel and the signal at each of these times. And up to sort of constant proportionality, this is effectively equivalent to computing the correlation between the moving average filter and the signal at each. Right, so higher values of the response mean that there's greater correlation at that point between the shape of the filter and the input signal, and values close to 0 suggest no linear association between the two. So we move along and we get at the end a randomly filtered output. And as I said, if we want to get different time scales, we just can dilate the kernels. So the kernels are dilated to be smeared across the space. You're going to capture lower frequency information and have the kernels narrow down, right? So bigger the dilation, the lower the frequency information you're going to be capturing, the higher the dilation, if you want to think about it that way, the more high frequency information you're going to capture. And so there's kernels at 3 different timescales, and you can see that the filtered output becomes more and more has become smoother and smoother in general because we are doing more and more low-pass filtering as a general. So the PPV feature that they mentioned is effectively just a proportion of the filtered signal that exceeds some threshold. So, for example, if the threshold is here, you just count the number of times the signal exceeds the threshold, and that would be the feature for that particular kernel. So you have a random kernel, you run it through, you randomly pick a bias, you get the proportion of positive values, which of course is related to the empirical CF, the signal. So the proportion of positive values here effectively gives you the probability that the filtered signal exceeds that value, the empirical probability. So you can think about this feature as capturing empirical quantum, sort of cumulative distribution information. And if you change the bias, you get different values of the proportion of positive values. So they were the two features they used, the maximum value and the proportion. And at the end, you take some total K number of random kernels, the default in the package is 10,000. So it generates 10,000 random kernels with random coefficients and random dilations, convolves the input signal with these 10,000, randomly generates biases to get PPVs, takes the max and you get 2K features. So by default, 20,000 features. And then this is the interesting, what I found very interesting, is the final classifier was just a simple, they call it the ridge classifier. It's effectively just using least squares, penalized least squares to do classification. So they have a linear model and they recode, you have multiple, your target has multiple layer classes, maybe 1, 2, 3, 4, 5, 6 classes. So they just do a 1 versus all classifier 5 or 6 times, recoding the outputs to be -1s and 1s. And they just use a linear ridge regression model to combine all the features together. So the penalty is an L2 type penalty, and the model was trained just using the squared error. And at prediction time, all we do is just compute the linear predictors for each of these models and pick the one that has the largest linear predictor value as the class that we're going to use. So what's neat about this, of course, is that fitting models with these squares is quite quick. Right? So compared to something like maximum likelihood for multinomial logistic regression, this is very quick. Especially quick, see later on, as we can exploit some aspects of linear models to make things even a little bit quicker. Now, I thought it was interesting that this works because, of course, L2 regularization is non-sparse. So I remember that when I became involved in this work, the first thing I thought was, well, why not be sparse? Well, you've got 20,000 features. So why not do something like L1? Some sort of sparse procedure. And it turns out that, well, I found it interesting initially that look, you can do some feature selection, but in general, it seems that you pay a much bigger price in trying to select the features than you do in reducing the variance from removing features that seem roughly irrelevant. So it seems that when we looked at it, it seemed that the features themselves, none of them in particular contributed a very large amount of information, but all of them contributed some small amount of information, which is actually, interestingly, the exact sort of situation where you want to do L2 regularization. Right? So L2 regularization is saying that the magnitude of the weights is very constrained, right? Because you're putting this squared error penalty on. So you're not allowing large variations in weights, which is the type of thing you'd expect in a sparse situation. Some strong predictors and weak predictors, irrelevant predictors. So the simple ridge regression model works really well. And later on, we've been exploring this a little bit more. I'm not sure I have time to get to that, but it does appear to be, well, yeah, some interesting results related to SVDs of this feature matrix is why I think the whole thing works reasonably well. But to put it in context, they then benchmarked on the UCR, and they get a prediction performance of about 0.865, so not quite as good as the deep learning models. But the whole thing takes around 2 hours to run because, well, now you just have a bunch of shallow network of simple random convolutions, quick to learn, and classifier is quick to fit, and prediction time is also quite fast. So they achieved near state-of-the-art performance at a fraction of the runtime, and in the community that was quite a big sort of splash. The paper actually has a large number of citations already. And I guess you might wonder why random convolutions would work particularly effectively. At least I did. And I guess, I mean, it's a little bit heuristic, a little bit hand-wavy, but if you think about it, you have a large neural network and you randomly initialize the weights as you must. And if the network is particularly large and you have a reasonable amount of regularization, then when you run your stochastic gradient descents, you wouldn't expect huge changes in the weights. So it seems very likely that if you have a very large network and you are fitting it after random initialization with a high degree of regularization, you're basically just ending up with a bunch of random weights underneath. The amount of change that you expect per individual weight would be very small when you have millions of weights and a large degree of regularization. So that's just a little bit hand-wavy. I'm not going to say there's anything formal yet in that, but that's a gut feeling as to why I think the random weights actually end up working, because I don't believe they're going to be fundamentally dissimilar, especially if you don't have enormous amounts of data to the weights you end up with after a small amount of training. But perhaps I'm wrong. That's just a conjecture. So that was the rocket scheme, and then I became involved. Primarily because Angus, the person leading the work, his other supervisor departed to go and work for the Australian Tax Office, and I was asked, in Monash, all students need to have at least 2 supervisors, so I was asked to be involved, and I became involved in the second phase of the work. So the idea here was that the rocket scheme seemed to work well, but perhaps wasn't super happy with the extreme randomness of the features. I mean, you get average performance if you run it many times, an average of about 0.68 or 0.86 around that. But individual runs on individual problems could actually exhibit a reasonable amount of variance depending on what particular filters you generated and what biases. So it's obviously a lot faster than the state of the art. So the whole run on 112 data sets took about 2 hours as compared to, say, 4 days for the inception time and 3 weeks for HIVE-COTE. So obviously it's substantially faster, but I did think we could speed it up. And the last problem here was that the schema does not produce probabilistic predictions, because it uses this linear regression approximation for classification, squared error. You don't naturally get immediately well-calibrated problems. So I'm going to first discuss I'll focus on the first 2 issues in this section, and if we have time, I'll at least give a sketch of how we solved the last issue. So the one thing was to note was that because the filter coefficients are drawn from normal distributions, they have quite light tails. So there wasn't a huge amount of variation within the filter between the magnitudes, as you would expect from a normal distribution. And I know that different distributions were tried, ones with heavier tails, ones without, and the whole scheme seems largely insensitive to which distribution you chose. So the first thought was that perhaps we could discard the random weights and reduce the whole problem down to just a binary number, right? So instead of having randomly generated weights for these filters, we just pick 2 values and use them as our random coefficients. So maybe we could say we have kernels based only on two values, say alpha and beta. And once you've done that, of course, generating random filters doesn't seem like much of a point, because you can just enumerate all the possible filters at a certain length that would have a certain number of alphas and betas. And that's what we decided to use. We said we're going to use our kernels are going to be all just permutations of weight vectors with, say, A values of alpha and B values of beta. So if we chose, say, A equals 6 and B equals 3, which is what the package uses by default, we would just have all the weight vectors would be permutations of this particular vector. So how would you choose A and B? Well, it turns out that the procedure is, again, relatively insensitive. It's very insensitive to a particular choice made. So what we did require, though, is that the kernels all sums are 0, so that the procedure is invariant to translations or level shifts of the input series. Now, perhaps for some particular problems, that may not be what you would want to do, but as a default, that's the choice we made. So if you add some constants to the input series, or different constants to each of the input series, the procedure is invariant. So I guess I should mention, I do want to make it clear here that I'm not claiming that this method of Rocket is somehow a universally best method for time series classification. Right? We all know that depending on the particular problems, you're going to want to use different types of features. But I do think it's very interesting how effective it is over a wide range of problems, such as simple setup. And it is very fast. So if we take one of the weights to be 1, without any loss of generality, it doesn't really matter when we choose how we would choose the ratio between the two. We can always set one to be equal to 1. Then, if we want our filters to sum 0, so that they're invariant to level shifts, we just need our beta to satisfy this simple relationship, which is minus the number of B's divided by the number of A's to choose our filters. And so you can think about A and B here being hyperparameters of the procedure. You can change A, you can change B. But it turns out that if you have one somewhat larger than the other, then you can get a big speed up. I'll see in a second. So in the end, we settled on A equals 6, B equals 3. So we had two values, alpha or weights, alpha of 1 and beta of -2. And we chose length 9 filters, but as I noted, it's in the paper as well. The ablation studies show that it's not particularly sensitive to any of these choices. So taking 6 values of 1 and 3 values of -2, we get these length 9 filters, and it results in 84 unique filters. So there are only 84 possible different kernels or filters in the system. And then we have log 2 of the length of the series, possible different integer dilations. So these are the total number of convolutions that we need to compute. So there's the example of what all the 84 unit kernels for the permutations look like. So these are our 84 different kernels that we are convolving with our input system. And interestingly, of course, once you restrict such a small set of kernels, you get an opportunity to make some optimizations. So the first is that we still generated, say, 10,000, that's the default, different features by taking 10,000 different values of the biases, but this time they're all generated, we're reusing the kernel. So in the previous scheme, each bias was associated with an individual unique random kernel, but here we have 84 times the number of dilations kernels, for many problems in the order of a few hundred, and we are reusing the output of these filters at different levels of the biases to get different values of this PPV, or proportionate positive value feature. We also made a small scale change to the way the biases were generated. rather than being sampled sort of without respect to the problem at hand, we now use, we sample from the output of some of the kernels to get sort of a automatic scaling variance. So if you scale the series up or down, the bias is just adjust accordingly. And we use some low discrepancy quasi-random sequence to allocate these biases out across the space to get rid of that level of randomness if you want to think about it that way. So now that each time you run the procedure, you get exactly the same output, unlike the original rocket where you run it, you would see a degree of variance even with the same number of filters. The other big thing was because weights, once we choose 1 and -2, are integers, so there's no need to actually multiply. So we can strip away all the multiplications and all the convolutions can just be done through addition, which made a substantial improvement in speed. And the final thing was that you can actually compute sort of a large proportion of all the convolutions in one hit at a fixed dilation level by exploiting the fact that you only have 2 different values of weights. So if you think about a convolution of a signal, say x and t, with a kernel, K filter, let's say, you can write it as taking your signal, multiplying it by the first weight, taking the signal, dividing it by 1, multiplying it by the second weight, taking the signal, dividing it by 2, multiplying it by the third weight, and so on. So you can sum down these delayed signals. So we've got this delay operator here, Z, which takes our signal X and delays it by, say, I time steps. And so you can think about your convolution as summing together a whole bunch of delayed time series, each one way. That's the usual sort of finite impulse response representation. So the neat kind of thing is that if you have a bunch of, say, the same kernel weights here, so say our kernel is this 1, 1, 1, 1, 1, and then 3 minus 2. So we're going to take the original signal, multiply by 1, delay the signal by 1 time step, add it to it, delay it by 2, add. When we get here, we're going to delay by 6 time steps, multiply by 2, and adding, and 7. So we can say that the convolution then is going to be the sum of the first of the time series here, delay 1, 2, 3, 4, 5, 6 times, minus 2 times the 3 delayed signals added for 7, 8, 9 delays. So we can then take this and add these 2 terms, add and subtract these terms here, which are just the sums of the time series delayed at times 6, 7, and 8. Nothing changed. And then we can take this, absorb it here, and what we end up with, we can absorb this here, we end up with the fact that all the convolutions can be computed by simply taking the time series, delaying it 9 times, summing that up, and then all the other filters are just selectively picking out or adding in some contribution from a couple of other terms. So if one of the weights is more prevalent substantially than the other, you get a dramatic speed up because you can compute, let's say in this case, 2/3 of each of the kernel in a single operation, and then all the remaining kernels are just summing or subtracting the excess terms. So all the convolutions are going to be just differences from this first term here, which we can compute once in each direction. So they were the main speed ups that we ended up with implementing, and then it was implemented in Python. And we still use the same linear classifier at the output, so it's still the same ridge classifier at the output. So first things, if we compare the new MINIROCKET scheme against the original rocket, so here we have classification accuracy of rocket, MINIROCKET on the 112 different time series in the UCR, we'll see that they're virtually identical. So reducing the space of kernels from this random space in this very small set of deterministic kernels appears to give very similar performance in classification. There is this one outlier here where MINIROCKET appears to be much better than the original scheme. That's actually just related to the way in which we switched to sampling bias terms. So in the original scheme, the biases were sampled sort of marginally without respect to the data, and on a couple of data sets, one data set could lead to some unusual performance. Once we actually implemented that scheme in the original rocket, this point went down here. So you basically recreate largely the performance. I mean, technically, if you go win, draw, loss, the new MINIROCKET scheme is better, but I mean, you look at that plot and they're virtually indistinguishable. However, in terms of speed, so here we have rocket, MINIROCKET. So we see that in general, not in general, MINIROCKET is substantially faster. For many problems, it was up to 10 times faster, but it could even be up to 100 times quicker than the original random convolutional scheme. So we made substantial speed ups. So the overall runtime on 112 data sets was down to 8 minutes. And compared to, say, 2 hours for Rocket, 4 hours for the deep neural net architecture, and 3 weeks for HIVE-COTE. And I'm not sure if I mentioned on the previous page, yes, so the overall classification accuracy for MINIROCKET was 0.872, so roughly in the same ballpark as the neural net scheme. And the proximity forest. So HIVE-COTE 2 is still the most accurate on these problems, but you would say that in practical terms, there is certainly some advantage to using a scheme that takes maybe 8 minutes to do all these rather than, say, 7 days. If we compare MINIROCKET against some of the other things that are the state of the art, so here we have the inception time, which is the deep neural net, rocket, MINIROCKET, proximity forest, HIVE-COTE, and some other techniques. So this is a plot of the mean rank of the method. So for each of the 112 problems, they were ranked by their average classification performance over multiple cross-validated folds, and this is a plot of their mean rank. So you can see that even the method that is the best, HIVE-COTE, is not uniformly the best in rank across all the problems. There's a number of problems in which it performs second or third best. So there's no clear uniform winner, but we see that the MINIROCKET scheme, despite taking, I think in this case, 3,000 times less time, is obviously competitive with the state of the art here. And look, the black lines here represent cliques of methods that are indistinguishable at some threshold from the, I think they use a Wilcox sign rate test, something like that. I can't remember exactly the details. It's not too important, but it gives you a rough idea of whether or not there's some form of significant difference between the procedures. I wouldn't read too much into the black lines simply because, well, they're based on a model testing correction. So the more methods you add, you can engineer these cliques to look how you wish, right? So, but you can see that there is the performance is certainly in the realms of the best performing method at a fraction of the computational cost. We also looked at how the method works on some larger data sets. So one of the problems with the UCR is that it doesn't have enormous data sets in it. Now, I'm not exactly sure why this is the case. One thing's for sure is that a lot of the methods that are running there potentially couldn't run in sort of a reasonable amount of time on sufficiently larger problems. And so we dug up some much larger problems. So we had these, in fact, they all appear to be classifying the sound, classifying the type of insect from wing sounds, which is something we managed to find from the biology space. So we had there this fruit flies insect sound, which is more generic, more different species of insects, and then various types of mosquitoes being classified by the audio produced by their wings. And so the largest one had 140,000 series, each around 4,000 long. And so, yeah, we just tested MINIROCKET versus rocket on these, and we see that you can make, even in this case, substantial improvements. So if you look at the mosquito data set, at a small loss of classification accuracy, the whole training procedure on the 140,000 series, or some subset of them, takes around 12 minutes and about a day, half a day roughly for the workers. So you could make some very substantial speed ups by reducing your set of possible kernels down to a small deterministic set. Really no loss of accuracy. So I thought that was, I mean, I think that's kind of interesting itself, right? So that you, perhaps in Spain, in light of this, there's been a lot of interest recently in these binary neural nets. So perhaps it's now not as surprising if you put it in that context, right? Because a lot of the binary neural networks are reasonably popular and they reduce the weight space down to ±1 or +1 -2, or some pair of weights. And the performance of these can be very good. So perhaps it's not that surprising that you can quantize down the weights into some minimal set. But anyway, at the time, this was maybe 3 years ago we did this. We thought it was quite interesting. But that was all that was required, at least to get decent performance. What's the time? So I think I'm going to have to call it there. I did have another section on using how you can convert ridge regression into well-calibrated probabilities in a very quick fashion, but unfortunately, I didn't present so quickly. So here we are. So thank you for your attention. I will jump to the end. There are some publications if you're interested, and there are packages available. Thanks for your attention, and I hope you found it at least somewhat interesting. Thank you.
Yeah, I have a very quick question. So thanks a lot for the presentation. And nowadays, for me, I don't have any background in time series classification, but I have some background in generation and forecasting. So if you stand at today's area, like people are more and more using transformer-based model. So if you look at back of this work, what do you think of those convolutional kernels? That is the advantages of those convolutional kernels rather than use those like multi-head attentional-based mechanisms.
Sure. So I guess I want to mention first of all that, careful I say, but yeah, so there is a lot of interest in obviously just transformer-based stuff and all the rest. And I guess I have noticed that a lot of the papers, the evaluations are often done in a very specific way, in the sense that non-deep learning methods are often simply not evaluated against increasingly under this assumption that if it's not a deep learning method, it can't be competitive, right? You'll see this is a very common thing. And I would say that a number of the methods that have been followed on, so for the inception tile architecture we used recreates the standard benchmark exactly. But a number of the papers since that have looked at things like transformers and others have used, well, if you read there, I can send you paper, but basically they use strange choices of subsets of the data and other things. So it's very hard to get a sense of actually how competitive the methods are. So we actually went away and took the rocket idea and just said, okay, how about if you just train a single convolutional layer network with fixed dilations? And you kind of get similar performance. I'm imagining there's a ton of interesting stuff in the transformer technology that you could use. I wouldn't be surprised if this wasn't something. I'm thinking that once you start to hit really large scale, then you'll be able to start to see the difference between, say, a shallower network and something that uses like this transformer techniques. I don't think that even the scale of a few 100,000 time series is a space where you're going to see substantial improvements, performance differences. But I think if you start working into millions or hundreds of millions of time series, I imagine it would be impossible that these methods wouldn't start to become the dominant paradigms. But what I think is interesting is, you know, if you look at this rocket idea, it was just taking multi-layer convolution networks and just reducing it to its absolute sort of minimum. And it performs very well. So my guess, I mean, I have no idea, but my guess is that these transformer-based techniques, there's probably very similar things waiting in them, right? That a lot of the stuff that's being done is probably irrelevant or redundant and can be stripped out. It's just going to take some of this function. I think that's kind of interesting, exciting, right? I like the idea of taking really complicated things and trying to make them simpler. But yeah, anyway, yeah, I'm not sure if I rambled a bit on that question or if I actually answered it in the end,
But very nice discussions.
yeah. But I do, yeah, I have noticed that it does seem to be a thing now that if you publish a deep learning technique, you just don't test against non-deep learning. There's this sort of unspoken thing that they obviously, they're the best, so anything else. And I can, if anyone's interested after, I can tell you a very amusing story involving a whole sequence of papers that were eventually beaten by a model that hit the mean. So, but no one ever tested against those benchmarks. So, but yes, cool. Thank you. Any other questions?
I think we are a bit running out of
Oh,
time.
good. If
But,
you're interested, you want to say
yeah.
hello, just come
Thank
on
you so
after.
much for the presentation and the interesting discussion, and thanks again.